Today we will begin Chapter 12 on chemical bonding. In this chapter, we are answering a very important chemistry question. Why do atoms stick together? Most atoms do not stay isolated in nature. Instead, they combine to form compounds and molecules, and those combinations are held together by chemical bonds. This chapter will focus on the main type of bonding, how electrons are involved, and how the arrangement of atoms give molecules their shape. Section 12.1 Objectives. In this section, we will learn how ionic and covalent bonds are formed. We will also study polar covalent bonds, electronegativity, and the connection between bond polarity and molecular polarity. These are important test concepts. From the worksheets and the chapter test, make sure you understand the difference between ionic, covalent, and polar covalent bonding, and how electronegativity helps predict polarity. Types of chemical bonds. A chemical bond is the force that holds atoms together and makes them function as a unit. Bond energy is the energy required to break a chemical bond. A stronger bond has a higher bond energy because it takes more energy to pull the atoms apart. In the picture, the image shows a water molecule model, reminding us that atoms are held together in molecules by chemical bonding. Ionic bonding. An ionic bond results when a metal reacts with a nonmetal. In ionic bonding, electrons are transferred. The metal loses electrons and becomes a positive ion, called a cation. The nonmetal gains an electron and becomes a negative ion, called an anion. Those opposite charges attract each other. The beaker of particles represents ions in solution, and the diagram below it shows that the metal transferring electrons to a nonmetal to form positive and negative ions. The main idea is electron transfer, not sharing. Covalent bonding. A covalent bond forms when electrons are shared by nuclei. This usually happens between nonmetals. Instead of one atom fully giving electrons away, the atoms share electrons, so each atom can reach a more stable arrangement. The diagram shows electron density between atoms. The key idea is that electrons are located between the nuclei and are shared. This is different from ionic bonding, where electrons are transferred. Polar covalent bonding. A polar covalent bond results when electrons are shared unequally by nuclei. One atom attracts the electron more strongly than the other atom. That means one side of the bond becomes slightly negative and the other side becomes slightly positive. The diagrams compare even sharing and uneven sharing of electrons. On this slide, focus on the idea that electrons are still shared, but not shared equally. That unequal sharing is what makes the polar bond. Electronegativity. Electronegativity is the relative ability of an atom in a molecule to attract shared electrons to itself. In general, electronegativity increases from left to right across a period and decreases down a group of representative elements. The periodic table image is there to remind you of the electronegativity trends. One of the most important takeaways is that the atoms near the upper right of the periodic table, especially fluorine, attract shared electrons strongly. Concept check. If lithium and fluorine react, which has more attraction for an electron? Why? If lithium and fluorine react, fluorine has more attraction for an electron because fluorine is much more electronegative than lithium. And a bond between fluorine and iodine, which has more attraction for an electron, and why? In a bond between fluorine and iodine, fluorine again has more attraction for an electron. Even though iodine has more protons, fluorine is smaller and its valence electrons are closer to the nucleus, so fluorine pulls more strongly on shared electrons. This is a very testable idea. A smaller atom in the upper right portion of the periodic table usually has a stronger pull on shared electrons. Remember this during assessments. Concept check. What is the general trend for electronegativity across and down columns on the periodic table? Explain the trend. The general trend for electronegativity is that it increases across the rows from left to right and decreases down columns. This trend happens because smaller atoms tend to have a stronger pull on the outer electrons. When explaining the trend, connect it to atomic radius and ionization energy. Remember, if an atom has a strong pull on electrons, it usually has a smaller radius, a higher ionization energy, and a higher electronegativity. Those trends are connected, not separate random facts. Bond polarity. The polarity of a bond depends on the differences between the electronegativity values of the atom forming the bond. If the difference is small, the bond is nonpolar. If the difference is moderate, the bond is polar covalent. If the difference is large, the bond becomes ionic, and we will not see any kind of electron sharing. The sequence of blue shapes shows the covalent and balanced electron density. When a polar covalent bond is seen, it has uneven electron density, and finally we see the ionic bond where electrons are effectively transferred. The picture is showing a continuum from equal sharing to complete transfer. You can think of it as a scale. Some literature uses charts like this to show the differences in electronegativity values, and it's an example that we'll be working later. You'll see that as they become larger in their difference, we will become covalent, where there's an even sharing, or close to even sharing, to polar covalent. There is a amount we will talk about. Usually the difference needs to be 0.1 or less, but that depends on the text we will be viewing. We will not need to memorize these kind of numbers. This would be a chart that you're given. One that you will probably want to start to know more by heart would be the electronegativity value of hydrogen, and then fluorine, that's 4.0. We'll get to the other ones, they'll be in examples. And then we can also just look at the periodic table itself and analyze it based on trends. We can also analyze it based on metal versus non-metal. All right, in this exercise, we will arrange the bonds from the most to least polar. In our first set, we have a nitrogen to fluorine, we have an oxygen to fluorine, and then we have a carbon to fluorine. Our second set, we have a carbon to fluorine, a nitrogen to oxygen, and a silicon to fluorine. And our third, we have a chlorine to chlorine, a boron to chlorine, and a sulfur to chlorine. You'll notice in this problem we will not be working directly with electronegativity values, but you should know that the most electronegative thing on all three of these examples is fluorine, and as we go down and to the left, we will become smaller in our electronegativity values due to the ionization energy. So if we were to rearrange A, we would get from most to least polar, we would have the carbon to fluorine, nitrogen fluorine, and then oxygen to fluorine. For B, we would have silicon to fluorine, carbon to fluorine, and then nitrogen to oxygen. And then finally for C, we have boron to chlorine, sulfur to chlorine, and then chlorine to chlorine. You will notice once we start hitting two diatomic elements, they will be as evenly shared as anything can be, with some very minor exceptions. Concept check. Which of the following bonds would be the least polar, yet still be considered polar covalent? Remember, the difference between polar and nonpolar is that nonpolar has an even sharing and polar has uneven sharing. So which of these will have a number great enough to be considered polar covalent? But also, do not forget, between a metal and a nonmetal, we are likely to see a non-sharing or an ionic bond. The answer is nitrogen to oxygen. Oxygen to oxygen is nonpolar because they are diatomic, bonded to itself, so their numbers would cancel out. Uh, Magnesium to oxygen is an ionic bond where metals lose their 2 electrons. It is in group 2, and oxygen being in group 16 will take both. Carbon and oxygen will not be polar. They are very similar in their values, and silicon and oxygen is a special case we will talk about later because silicon and oxygen do not typically bind 1-to-1. We will likely see 2 oxygen, so silicon dioxide, so we'll see that one as we go further. Which of the following bonds would be the most polar without being considered ionic? The answer would be silicon oxide. We're looking at the largest electronegativity difference that still stays in the polar covalent category. The cutoff for us will be an electronegativity of 2 or greater is typically observed as ionic bond, where 0.4 to around 1.7 are polar covalent. And when we get to the small fringe cases in between, we will talk about them. Bond polarity and dipole moments. A dipole moment results when a polar molecule has a center for positive charge separate from a center for negative charge. This means that one part of the molecule is more electron rich and the other one is more electron poor. The image shows a bond with a plus sign on one end and a partial negative region on the other, and an arrow pointing towards the more negative side. That arrow represents the dipole direction. Water molecule dipole moment. Water is a classic example of a polar molecule. Oxygen attracts electrons more strongly than hydrogen, so oxygen becomes partially negative and the hydrogens become partially positive. On the left, the water molecule is labeled with partial charges. On the right, the positive and negative charge centers are shown as separate locations. Because water is bent, the bond dipoles do not cancel, so the whole molecule has a dipole moment. Why water polarity matters. The polarity of water affects its properties. It helps water remain liquid at higher temperatures than you would otherwise expect, and it allows ionic compounds to dissolve in it. The image shows water molecules interacting with one another. The key point is that polar molecules attract each other. Water's polarity is not just a diagram issue, it explains the real-world properties of water. (12.2) In this section, we will move beyond bond type into ion and ionic compounds. We will learn about stable electron configurations, how to predict formulas of ionic compounds, the structures of ionic compounds, and factors that affect ionic size. These are important because the test bank asks about common ion charges, ionic formulas, and ion size comparisons. Stable electron configurations and charges of ions. This slide is a visual summary of common ion charges by group. As we have learned, group 1 are metals that will form +1 cations. Group 2 metals will form +2 cations. Aluminum in group 3 is the one that will form +3 cations. The group 7 nonmetals form -1 anions. And group 6 elements will always form -2 anions. This slide is another visual slide that supports predicting ion charge by noble gas configuration. The table lists formulas for ions, the way that atoms gain or lose electrons, and the resulting noble gas electron configurations. It is showing that ions often form to reach noble gas configuration. For our emphasis, the main takeaway is not memorizing the whole periodic table. The main takeaway is that metals usually lose electrons. Remember, cats are losers. And nonmetals usually gain electrons. Onions are delicious and yummy. And the goal is that a stable electron configuration is reached. Atoms in stable compounds usually have a noble gas electron configuration. Metals lose electrons to reach a noble gas configuration. Nonmetals gain electrons to reach noble gas configuration. This is why sodium commonly becomes Na+, magnesium becomes Mg2+, chlorine becomes Cl-, and oxygen becomes 2-. This is our common prediction skill that we have been using and will need to relearn. Predicting formulas of ionic compounds. Chemical compounds are always electrically neutral. That means the total positive charge must equal the total negative charge. The table at the bottom shows group numbers, common ion charges, and resulting electron configurations. Use this idea to predict formulas. For example, magnesium is 2+ and chlorine is -1, so the neutral formula is MgCl2, not MgCl or Mg2Cl. Ionic bonding and structures of ionic compounds. Ions are packed together to maximize their attractions between oppositely charged ions. Ionic compounds form crystal lattices, not individual little molecules. The image shows the repeating three-dimensional array of positive and negative ions. This matters because one of the questions that we will ask later, students incorrectly think sodium chloride is made from separate NaCl molecules, and it's not. It is actually a crystal lattice structure as seen in B and A. Ionic size. Cations are always smaller than the parent atom. Anions are always larger than the parent atom. When an atom loses electrons to become a cation, the electron cloud becomes smaller. When an atom gains electrons to become an anion, the electron cloud makes the ion larger because there are now more electrons repelling each other. The blue spheres on the left and the pink spheres on the right compare the size of atoms and their ions. Focus on the trend. Lose electrons, get smaller. Gain electrons, get larger. Ionic compounds containing polyatomic ions. Polyatomic ions work together in the same way as simple ions. The covalent bonds hold the polyatomic ion together, so it behaves as a single charged unit in an ionic compound. The example on the slide is ammonium, NH4+, and nitrate, NO3-. Each polyatomic ion has covalent bonds inside of it, but the whole group acts as one ion when forming ionic compounds. Section 12.3. Now we will begin with Lewis structures. In this section, we will learn to write the Lewis structures and then extend that skill to molecules with multiple bonds. This section is heavily tested. Students should be able to count valence electrons, should have a good idea of what the central atom is, should be able to draw bonds, fill octets, and recognize resonance and common exceptions. Writing Lewis structures. When writing Lewis structures, we include only the valence electrons. The most important requirement is that atoms achieve a noble gas electron configuration when possible. This is the octet rule, with hydrogen following the duet rule, as well as helium, although we won't really see that in any of these. The slide shows an example of atom symbols with valence electrons highlighted. The key message is that core electrons are not part of the Lewis structure because they are not involved in bonding. Bonding pairs and lone pairs. Bonding pairs are shared between two atoms. Unshared pairs, also called lone pairs, are not shared and not involved in bonding. The examples on the right compare hydrogen, fluorine, and fluorine molecules. The point is to show that electrons can either be shared in a bond or remain as lone pairs in an atom. Shared, lone pairs. You'll notice if there are two atoms and they're bonded together, they can have two, or potentially if there's a double or triple bond, more shared electrons. Writing Lewis structures. This slide is very visual but very important. You'll notice on the top Lewis structure we have bonds and then lone pairs. The lone pairs added up with the bonds will complete the duet rule for hydrogen and the octet rule for oxygen, with a total of 12 electrons. This image is to reinforce how we use Lewis structures to visually track shared electrons and lone pairs. Lewis structures with molecules of multiple bonds. We can have a single bond with one shared pair of electrons. A double bond shares two pairs of electrons, so 4 bonding electrons total, and a triple bond is 3 shared pairs of electrons. That would be 6 total shared electrons. Resonance. A molecule shows resonance when more than one valid Lewis structure can be drawn for the molecule. In the picture, you'll see 3 different structures with alternating placements of the double bonds and the electrons. The idea is that the molecule flips back and forth as at different times. We call that resonance structure. And they are all valid ways of showing the distribution of that electron. Some forms may be more stable than others, but for the most part, we just want to be able to show that different resonance structures exist. Exceptions to the octet rule. You knew they were coming. Boron is a common incomplete octet example. Some molecules contain odd numbers of electrons, such as nitrous oxide, nitrogen dioxide, and they do not fit the standard octet pattern. In the picture, you will see a BF3 diagram, which shows boron with fewer than 8 electrons around it, if we count 2, 4, 6 shared electrons between it. It's worth knowing, but the basic Lewis structure is still more important than memorizing our exceptions. Concept check. We'll be drawing a Lewis structure for each of the following molecules. Remember that hydrogen only has 1 electron. Fluorine has 7 electrons. And together, we will make something different. So let's start with just H2. If I have a hydrogen, I'm going to put a dot here. And I have another hydrogen, dot here. To complete the duet rule, both hydrogens are going to need to come down to form a bond with each other, which would result in a Lewis structure that looks like this. Imagine that's a straight line. For fluorine, I will do much of the same. So I'll start here, but fluorine has 7 electrons. So remember, we fill these electrons one at a time, clockwise, until we have to come back. And there we have 7. So I'll be putting them together. So I'll need to draw another one. I'll go clockwise. And then you'll notice both fluorines have one set of electrons that are alone and could satisfy the octet rule with each other. So to redraw, let me get rid of these lines. I will replace my electrons here and then put my dot here and dot here to represent those single electrons now, and they can come together to form that bond. And then finally, for my hydrogen and fluorine bonded together, remember hydrogen is going to have that 1 electron. I'm going to start it over here since we already know how that's going to work. And I'll put a fluorine here. And we'll follow our rule, but I will put it on the left so it's easier to work with. And then you'll notice we have electrons that could complete each other's rule. So I'll do that. And then I will connect them, showing that they are sharing electrons. Concept check. Now we'll do the same thing, but for nitrogen, carbon, chlorine, oxygen, all of those we will need to look up on our periodic table. So nitrogen is going to have 5 electrons. Hydrogen still has 1. That's easy. Carbon is going to have 4 electrons. Chlorine is in group 17, just like fluorine was, so that one is also going to have 7 electrons. And oxygen is in group 16, so it will have 6 electrons. All right, so let's start with nitrogen. If nitrogen has 5 electrons, let's draw that all on its own first. 1, 2, 3, 4, 5. All right, remember hydrogen needs to complete its duet rule, while nitrogen needs to complete its octet rule. If this was NO or NO2, we would have the exceptions to talk about, but it's not. So I will put my center electron working element here in the middle. I will put my electrons around it, and then I will on each side put a hydrogen. Why am I putting them on each side? Well, those electrons are happy all on their own. That lone pair won't be working with the bonds. Remember, all these hydrogens have one electron, so I'll put a dot next to all of them. And would you look at that? If we draw a line between all those, ammonia is quite easy to draw. That is our Lewis structure. I'm going to clear off some space now. All right, our next one we're going to be working with is carbon dioxide. We talked about this a little bit at the beginning of the year. So if you remember, this is going to have some resonance structure. You might be wondering, how do I know which one to place in the center? And a lot of that comes down to memorizing some basic rules. But oxygen would not likely bind with itself if it has the option to bind with carbon. All right, so carbon has 4 electrons, easy enough. And oxygen has 6, so we're going to put those to the left and right. 1, 2, 3, 4, 5, 6. Put oxygen here, just pretend that's a real circle. I'm going to put that there. All right, so you might start to see an issue here. It doesn't immediately seem like we'll be able to complete the octet for any of these. But this is where we need to go back to being able to use double bonds. So if I look at, and I'm going to use the highlighter here, if I look at this electron on each of my oxygens, and I look like I erased an electron, so I don't want to do that. You'll notice that I have corresponding electrons that are available on my carbon. So for this, we will actually be switching over to this, and we will want to draw it something like this, where we have double bonds. Oh, hey, and you're going to want to pay attention to where you have your double bonds. Don't make that mistake. I almost did. Just like that. And again, let's do it more cleanly than I am with my mouse right now. And you will see that we still have these electrons that are lone pairs that are not participating in bonding. But the cool thing here is that it is possible to draw a resonance structure where I have a triple bond to an oxygen and a single bond to an oxygen. We will not be looking at that resonance very frequently. We would have to talk about where electrons go, because obviously if we've got electrons there and here, then that can't work because that's more than 8. So we will get to that in another example. And then finally, we should probably all be able to see what's going to happen with the carbon and the 4-chlorine, because chlorine, of course, if we look up at the top, we have 7 electrons, and carbon has 4 electrons around it, so the center molecule or atom will be our carbon, while the top, bottom, left, and right will be chlorine. So let's draw it without putting the electrons in first, other than on my carbon. Chlorine, 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 and chlorine. And now each one of these gets 7. So 1, 2, 3, 4, 5, 6. And I'm going to break the rules for counting, and you'll see why. All right. And if you can see why, you'll know why I said we start by learning how to do it clockwise, and then you can stop doing that once you are aware of all of your electrons. So that becomes a bond, this becomes a bond, that's a bond, pretend those connect, and then that's a bond. So there we have our Lewis structure for that molecule as well. Remember, we will have to learn our naming rules again. I know you all love those. So carbon is on its own, and the center, it's also the first, so that's just carbon. But then we have 2 nonmetals, so that'd be carbon tetrachloride. Remember, tetra is 4. We'll come back to naming as well, so if you forgot all of your roots, it's time to start learning them again. Here's our final concept check for the Lewis structures. Now I'm going to do this one a little bit faster now that we have looked at all of these already. We will have to eventually start talking about the shapes of these, but for now, I'll just start with carbon to oxygen. Now we know carbon has 4 electrons, right? So we can go like this, and we know oxygen has 6. And I drew them like this for a very specific reason. So you'll see up on the top and the side, or really from any of these, it's going to be very hard to make an octet, but there is a way. And this would be how we would complete this. This is one option. Another one would be C with a triple bond to oxygen, and then both would need a set of electrons as well. We'll talk about this one more when we get to one of our group worksheets, but you'll see that one in action. All right, now let's move on to our organic molecule here. We've got a methanol. If you want to take organic chemistry at some point, you'll learn those names. But it's not fun all the time, so maybe don't worry about that right now. All right, so we've got carbon. It's got 4 electrons. Easy. It's got hydrogens on it. Got hydrogen on it. We got a hydrogen on it. But we have a couple problems. Where does the O go? Where does the H go? On organic molecules, this is my main substituent. This is my what the structure is based off of, and then this is my side chain. It's got some other names too, but we don't need to worry about that. So we know that there will be a connection from the carbon to the oxygen and not the carbon to another hydrogen, because remember, it can only have 2 electrons. So if I bond there, I also am going to have to bond to this. And when I do that, it's usually easier than trying to put the electrons out first and then figure the rest of it out later. So I know it had 6 electrons. This shared 1, this shared 1, so I can draw the other 2 like this. That doesn't necessarily mean that that's its 3-dimensional structure, but that's okay. We'll work with this for now. All right, and then our last one. You'll notice it has a minus, which should throw some red flags for you. You're going to have to do something special on this, and that is add in 1 extra electron to complete an octet, but it's going to look a little different. All right, so we've got an oxygen, we've got carbon, and we've got a nitrogen. Nitrogen has 5 electrons, carbon has 4, and oxygen has 6. All right. Now let's see how can we do this. Now we know that this and this can connect to make a bond, or they can exist together. They don't connect, but it's the easy way of writing it. We can take this electron and do the same thing. And now we have a double bond for the oxygen to the carbon. But then what about the nitrogen? It does something a little weird too. So I've got these 2 electrons. I've got no way to satisfy the octet for the carbon other than doing another double bond. So let's highlight the electrons that we're going to use. It's that one, this one, and this one. Again, it doesn't matter if it's one of these 2 or that one. It just isn't going to be this lone pair for different reasons we'll talk about later. So I'm going to come by and I'm going to draw those in. All right. So there we go. So now we've got, let's see, 2, 4, 6, 8. The oxygen, happy. Carbon, let's see, 1, 2, 3, 4. So that'd be 8. And then let's check the nitrogen. 1, 2. Based on my count, I've only got 7 electrons over here. Let me make sure we all agree. 1, 2, 3. This counts as 2. This counts as 2. So it's 1, 2, 3, 4, 5, 6, 7. And I don't think that's going to work. But you'll notice we've got a minus right here. That means for this entire molecule, I have an extra electron from somewhere else. Do we need to know where? Nope. But there you go. Now we have two lone pairs, and then when I have some kind of molecule that has a charge, whether it's a positive or negative, I do this on the outside. That lets the person who's observing it know that, hey, we added that electron. All right, 12.4, also known as the hard part. We will be shifting from the structure to the shape. In this section, we want to understand the molecular structure and bond angles. We want to predict molecular geometry from the number of electron pairs and apply the VSEPR model, including to molecules with double bonds. This is probably the hardest and more tested areas for the entire chapter. Molecular structure. Molecular structure is the three-dimensional arrangement of atoms in a molecule. Water is shown here as an example of a bent molecule with roughly a 105-degree angle. The slides show the ball and stick style model of water and the bond angle. It's important that molecules are not flat when we draw them on paper. We want to actually look at their three-dimensional layout to be able to use them in better explanations of mechanisms. Linear structure is the easy one. You'll be happy when you see this one, something like carbon dioxide. It is where everything is arranged in a line. We have, if we do the Lewis structure, two double bonds in the oxygen to carbon and then the other carbon to oxygen. So they're in a straight line. Even though each carbon to oxygen is polar, the whole molecule is symmetrical, so the dipoles cancel out and it makes carbon dioxide non-polar overall. It also is straight, so it's 180 degrees. We should all know that one. Our next one is trigonal planar. A trigonal planar molecule has three regions of electron density around the central atom and forms angles of about 120 degrees. BF3 is the example we're using here. The model shows boron at the center with the three fluorine atoms arranged at a flat triangle. The 120-degree angles are labeled on the image. See that? So between each fluorine group, there's 120. We add those all up, we get our 360. Triangle, plane. This is all flat together. Tetrahedral. This is the one that'll typically catch people up. A tetrahedral molecule has four regions of electron density with a central atom and bond angles of 109.5 degrees. Methane, our fuel, is our best example. It shows methane in both a model and line drawing and then the angle that we can see in between each version. You'll notice that one of them is toward us, these two are somewhat in plane, and then that one is going upward. So we end up making a tetrahedral. The VSEPR model. VSEPR stands for valence shell electron pair repulsion. The main idea is that electron pairs repel each other. Remember, they're all negatively charged and in opposite sides of their orbitals. So molecular structure is determined by minimizing repulsions between the electron pairs. This is the rule students should remember. Electron groups spread out as far as possible around the central atom to try to minimize repulsion. Two pairs of electrons. With two pairs of electrons around a central atom, the arrangement is linear with a bond angle of 180 degrees. BeCl2 is the example shown. The Lewis structure of the model is shown with the atoms in a straight line. The slide labels the 180 degrees and the word linear. Very important. 180, remember, equals linear. Three pairs of electrons. With three pairs of electrons around a central atom, the arrangement is trigonal planar with bond angles of the 120 degrees. BF3 again is our example. We'll see both drawings. You can see that we are 120 degrees still. And if we see 120 degrees, we should be trigonal planar. With 4 pairs of electrons, we can have something like methane, where we have bond angles of 109.5, and that will be tetrahedral. So here is the best way to explain the VSEPR process. Our first step will be drawing the Lewis structure. Our next step will be counting the electron pairs and arranging them in a way that minimizes the repulsion, so we put them as far as possible. And then we determine the position of the atom where the electrons are shared, and then we name the structure from the position of the atoms. All right, and then here's a brief summary of everything we just talked about. So if we have 4 bonds, we are likely to be tetrahedral. We don't really have anything else we can call that right now. If you have 3 bonds, you're between trigonal planar and tetrahedral. If you have 2 bonds, you could be either linear or tetrahedral. And then if you just have 1 bond, believe it or not, you're also linear. We won't talk about that one. Molecules with double bonds. When we use the VSEPR model to predict molecular geometry, a double bond is counted the same as a single pair of electrons. In other words, a double bond counts as an effective 1 pair for geometry. This is important because students often mistakenly count a double bond as 2 separate directions in space. For geometry, it's 1 region of electron density. All right, for our final concept check, we will need to determine the molecular structure and include the bond angles for HCN, PH3, and our carbon tetrachloride. HCN is going to end up being linear. Let's make sure we know why. Let's try this. Hydrogen is going to have R1, carbon is going to have 4, and then nitrogen is going to have 5. The only way to make this work is for these 3 electrons and these 3 electrons to make a triple bond, and this to make a single bond, which would end up looking like this, with electrons over here. That does matter now because they, again, want to be as far away from the rest of these electrons because they repel each other. The angle here is 180 degrees. We had, remember, this only counts as 2 bonds when we talk about the Lewis structure when we start doing the actual physical outline. So that's all in a line. The next one, PH3. So we're going to have a P, have 1, 2, 3. So this one is actually not in the plane. We'll talk about that one a little bit later. But this is roughly the layout. But then we'll have 2 electrons pushing somewhere. Whether we draw it like this or we put the hydrogen down here, it doesn't ultimately matter. But this will end up being our 107 degrees. Now this one is specific to PH3, so as long as you know it's somewhere between 109.5, that's all that I need. And then our last one, this is just like methane, so if we go like this, and that one's coming down. I'm not going to draw all the electrons on the chlorines, but remember they have 7, so if they share 1 with that carbon, they're happy. And then this one will end up also being 109.5. But it is the other shape because there are 4 substituents. That's how we get that tetrahedral shape. This part is a lot of memorizing the different structures you can have and then analyzing our bonds. We will do a lot of this in class with a lot of worked examples. Good job making through it.